Hello, in this video we'll be looking at Coulombs law and the electric field. So, let's have a look at Coulombs law first of all. Let's say you've got 2 point positive charges. One here at positive Q, positive charge, and one here also positive Q. Okay, let's draw this a little bit bigger to see. So it's, there you go. And they're both positive. Now, due to Coulomb's law, these two like charges would feel a repulsion. That would feel a force acting in that direction of F, and this one would feel an equal and opposite force of F as well, and that's obeying Newton's third law. And the magnitude of the force they both would feel is an inverse square law. So let's say the distance between these points is a distance r, would be equal to, first of all, q squared if they're both q's, or q times q for the same magnitude of charge, divided by the distance between them, r squared, multiplied by a constant k. That could be written now k is a constant, is equal to 1 over 4 pi epsilon, where epsilon is permittivity. Now for electric fields in air, and we call this the permittivity of free space. So in air we'd have 1, which is what we use mostly in most syllabuses, will be 1 over 4 pi epsilon naught, whereby epsilon naught was equal to 8.85 times 10 to the minus 12. Okay, so another way we could think of writing this, we could call that Q1 and Q2. So the force would be equal to K Q1 Q2 all divided by r squared. Okay, let's rub that off. Okay, now if it was a positive and a negative charge, that was Q positive and Q negative, the forces would still be equal and opposite, but they would be attractive like that. Now, around this point charge, there would be an electric field. So let's start with a positive point charge, so that's Q positive. There would be an electric field around it, and the electric field, if it's positive, would act out radially. Okay, so this is the electric field acting out radially. Now, if there happened to be a small positive charge, this charge would feel, let's call that Q plus, and this one big Q plus. This charge would feel a force acting on it, and the magnitude of the force would be equal to the charge, which is little q, multiplied by the electric field strength. So therefore the electric field strength can be defined as the force a small positive test charge would feel per unit charge. Okay, so for instance, therefore, if we combine the idea of Coulomb's law, so if there was this Q plus and Q minus, so if that was Coulomb's laws, big Q times little q times a constant divided by the square of the distances between them. And if that the electric field we force per unit charge, the electric field strength around it would be equal to the constant times q, so we're dividing by little q, all divided by r squared. And this would be the electric field strength. Now, so far we've been talking about small point charges. Okay. Well, the same applies for spheres. So, if we were to draw this as a sphere instead, using hollow spheres, as in the Van de Graaff generator, so this is a hollow sphere, and if it's a positive q, now there would be actually no charge at all in the middle, but it would act as if the electric field was pointing out from the very middle. Although within the sphere there's no charge at all, you would get this, and that would be acting on a positive charge within the area around it, and then again that would feel a force, and the force would be equal to Q times the electric field strength. Now, the electric field strength is greater towards the sphere, and it's greater by the closer the lines are together. So you can see out here, there's a point out here, you see the electric field, let's extend them, because they carry on out. That would be, the electric, those would be further apart, but there's another point, say, point R, let's say, another point called P2, let's call it P1, that would feel a greater force, the greater electric field strength, because those lines are close together. Now, in the case of negative, let's point charge off sphere, let's draw a negative sphere, Q minus. The field lines, because it is attractive and on a positive charge, the field lines would in fact act towards the center like that. So the electric field lines would act like that because a small positive test charge would in fact feel a force acting towards the center. So imagine this is our small test charge, and the lines would they're acting towards the middle, but they would stop because there is no electric field in the center, and the maximum electric field strength is on the surface of the sphere.